cluster. Okay. Okay, so first of all, let me thank the organizers for the invitation. It's been a very nice program, and I'm pleased to talk in it. And so my focus here will be mostly on these clustering techniques, right? I will use the minimal composite Higgs model as an example of how you could apply this, but the focus is more on the technique than on the model itself, right? So this is the obligatory problems of the standard model slide, right? It's probably not needed with this crowd, but it's important to keep, I mean, there are some students, so to keep the students motivated, right? And it's clear, despite the new physics not showing up in the LHC like it was supposed to at some point, right? We still have all these questions that are unanswered, right? And the answer to most of these questions can only come from particle physics, and you cannot say that particle physics is done unless you're satisfied with I don't know, right? And so there's a lot to be done still. Right? And how do we approach most of these problems, right? The solution to the majority of them involves extending the standard model in some way, right? You build a bigger model, right? And you try to fix one or more of those shortcomings at the same time as you keep the standard model, the parts of the standard model that work well, right? So theoreticians always liked this first class of models, right? So we love models that can be extended all the way to the Planck scale. And so a lot of the theoretical work focused on these UV complete models for a long while, right? In contrast to that, most of the experimental searches are focused on pretty simplified versions of those models, right? Usually you choose like a very convenient Poynting parameter space that gives you a clear phenomenology. And this is the kind of phenomenology that has been mostly excluded by experiments so far, right? The simplified versions of these. There's another class of model that is not exactly UV complete, right? But solves the problems you want to solve, the hierarchy problem, for instance. You push these problems to a higher scale, you find a model that is a continuation of the standard model up to some other bigger scale, but then you need yet another UV completions. And there are some examples of these, and I'll talk a little bit about the composite Higgs models that falls into this category, right? And of course, you can always go the agnostic approach, right? And just build everything you could possibly build with the matter content that we know, right? And parameterize these in expansion. That's what you do in effective field theories, right? So there's a lot of work in that. That's probably the most active area nowadays, both from the point of view of experiments and theory, right? So there's a lot of people working on these EFTs. So the problem you're usually faced with in these extensions of the standard model is that the parameter space is quite big. Usually you have a lot of free parameters, right? On top of all of those parameters that you already had on the standard model, right? Those are fixed mostly, but you have at least many times doubled or tripled the amount of parameters. And you have to deal with this big space of models, right? And just to give an example, this is a Lagrangian for one of the implementations of the minimal composite Higgs model, right? And only these two parts of the Lagrangian already bring us all these free parameters, right? So usually these spaces are quite big. So what we do about that, right? Before. Also, another complication is that these parameters in the Lagrangian are not straightforwardly connected to the observables. Right? We know that the parameters in the Lagrangian will then lead to, say, a mass matrix. So you have to diagonalize, find couplings, find branching ratios, widths, all of that. Right? And even that, those that we could call the physical parameters of your model, are not still the observables, at least not directly, right? What's really observable is these distributions you get on your detector. So how can you approach the problem of having too many parameters there, right? So what we usually do is it's like you can like arbitrarily divide in two classes of approaches, right? One thing you can do is use additional constraints to reduce the dimensionality of your model, right? Like, for instance, I don't want any CP violation, so I can make some of my parameters real, right? Get rid of complex phases, right? I can assume some flavor universality between couplings, and that reduces the flavor space, right? You can reduce the dimensionality. Another thing that you can do is look for convenient phenomenology, right? So you walk on the parameter space of your theory and you look for points that are especially easy to find. So just one light resonance, nothing else, very narrow. If you're looking for dark matter, you make it long-lived, right? So you basically, guided by what's easy to find, you reduce your space to a corner where you can easily look for, right? We make a lot of jokes about this, right? You're looking under the lamppost, but that's actually the right approach, right? If you have things that are easy to look for, those are the first things you should look for, right? And if you're lucky, right, jackpot. We were not lucky, right? So the easy things to find are already excluded, right? So now you have to look away from the lamppost, right? And then you have a problem, right? Because then you have to brave this multidimensional space, right? And this is quite doable if you can get a lot of manpower on a particular model, right? You can do these very complicated, work-intensive global fits, right? And that's what's going on essentially in the effective field front, right? Because then you can motivate a lot of people to get involved. That is pretty model-independent way of approaching things, so everyone can get on the same boat. Now, when you go to specific models, right, the sociology of it is more difficult, right? It's hard to convince a lot of manpower to be dedicated to one specific model. Even if you try to make it a class of models, that can be hard, right? So in a way, you have to find a way to attack these, if you want to put constraints on more complete, not so simplified models, right? You have to find ways of doing that in a smart way, because you won't have that much manpower for each of these particular models, right? And so this clustering technique is one way of trying to do that, right? So clustering fits into a bigger ecology of non-supervised machine learning algorithms, right? This is not what we usually call machine learning, because there's no adaptivity to it, right? But it's a pattern recognition algorithm, right? You're trying to use the computer to find patterns for you and divide a big population of things into groups, right? Which we call clusters, right? So the idea is to, in our case, to scan the parameter space of your theory. Here I'm representing this as a 2D plane, but it's really a multi-dimensional thing. So this third axis represents all the other parameters of your model, right? And group these points in parameter space into clusters guided by phenomenology, right? Essentially, you have a choice here. You can try to make these groups based on masses and widths and I mean the physical parameters, but in fact you can also go straight to the observables, right? Since you're using these techniques, you can actually do this grouping by the observables. And that's what we're going to do here, right? So this was first. Additionally, once you do these groupings, right? Before I forget, once you do these groupings, you can also within each cluster, right, look for a point that is I'll define that better later, but which is the most similar points to all the others in the same cluster. And this guy becomes a representative in terms of the distributions it generates, right, to the whole cluster. And that's what we will call a benchmark point here. Right? So you can use the same criteria to choose one point within each cluster, right? And that's the point we want, right? You can then design search strategies around these benchmark points. Right? So this was first proposed in this paper, right? And the idea here is to do a beam by beam comparison of curves, right? So here I'm just taking any random distribution. This is the PT of the Higgs in some model, right? In fact, the MCHM model, right? And the red curve is the standard model, and the other three are three different points in parameter space for the MCHM5, right? And what we'll do is compare these curves and see how similar they are to each other, right? So we can do that easily, right? By eye, everyone here would agree that curve P1 here is more similar to curve P2 than they are to the standard model, right? But then make clear that you want this yellow area here to be as small as possible, right? If you're doing a beam by beam comparison, right? So in this paper, they propose to use this log likelihood ratio as the measure of difference between those curves, right? So NA and NB here are the number of counts on a particular beam. So I is running over all the beams, right? And I go beam by beam and I calculate these. These are just the number of counts in each of them, right? And A is one of we call this sample, right? One of the curves is sample A, the other curve is sample B, and I can compare a lot of these curves and always find this number TSAB for any pair of distribution, right? So this has a few very useful properties, right? This is like the distribution of these log likelihood it's chi-square-like in the sense that it's univociously growing as the difference between the curves grow, right? But in this case, in the negative direction. So equal curves will have a TSAB which is 0, right? And the more different they are, the more negative this number will be. That means if I take one particular curve, compare to every other point in my perimeter space, I can order all these other curves by similarity to that reference one, right? So that's what we will use to judge similarity. And so the bigger this number, right, the more alike they are. And so that's what I'll use, right? Also, this has another advantage. Since I'm doing a beam by beam comparison, right? And these are two distributions from the same simulation. So this red curve here and here was generated by the same simulation, right? I can actually use more than one distribution as a criteria. Right? All I have to do is once I sum this last beam on this distribution, I start summing the next one on the other distribution and take the two of them into consideration. So I can play with that. I can try all the different kinematic distributions I have in my simulation and see which ones discriminate these clusters.
Shouldn't they be all correlated?
They will be correlated, and you can actually notice that. And so in the case I will look here specifically, I stopped at parton level, so I have to fill final states, right? So at some point, putting yet another distribution and yet another distribution, that changes nothing in your cluster. And that's a manifestation that you're not putting new information. So in the end, if your final state is not very rich, right, just taking one, maybe two distributions is enough to saturate the thing, and then changing them doesn't do anything, right? So it becomes independent of this particular choice.
Why would you do it as a series of 1D distributions rather than a multidimensional one?
Well,
you could compare like 2D or 3D distributions, right?
Oh, in this case, yeah, you could. In principle, you could. You have to order them in some way, right? In the end, will be a one-dimensional sum. Anyway, but Yeah, yeah. The question that comes to my mind is there any new information in that? Right? Maybe a dilate plot-like thing could...
Because that would have the correlations, while if you do just one-dimensional slices, you don't necessarily see correlations.
Yeah, maybe. Yeah. I didn't try, so... yeah.
I mean, it can only improve whatever you do.
Yeah. So, with that in mind, right, let the clustering begin. So what we do, right, the first thing is to simulate a whole lot of points. So you have to make a big scan of your parameter space, take every one of these points, go to MATGraph. If you're going all the way to final states, you have to do Pythia, Delphis, whatever, right? In this case, we just use MATGraph, right? And you have hundreds of distributions, right? All the distributions for each of those points. Then you start by calling each point a cluster, right? That's the most ridiculous thing, but you start with the same number of clusters that you have of points you generated, right? And then you build a big matrix, right? Essentially, you're just taking every point and calculating the TSAB with every other point. That's the most intensive part of the calculation. But once you have these big matrices, you know who is similar to who, right? And then you just look for the smallest number in that matrix, right? That's the guy that will be the most similar, right? You just look and you cluster, right? You find the two guys that are most alike and you put them in the same group. Right? And then you do that interactively, right? You look for the highest TS-mean and you group again and you group again, and every step you take reduces the number of clusters by exactly one. Right? You're just grouping them together. And when you have to compare two clusters, now that the clusters have more than one element in each, you compare every guy in this cluster to every other guy in that other cluster and take the worst case. Right? If that worst case is still more similar than any other point outside, I merge these two big clusters. Huh? And of course, you're not doing anything at this point because the matrix is ready. The computation now is really simple, right? You have all the numbers already of similarity between these clusters. Huh? And then you have to decide when to stop. That's the tricky part. That's where it's not artificial intelligence anymore, it's natural intelligence. Right? You have to look actually at what's happening and avoid, of course, two situations. There's one ridiculous one where I started, where you have a huge number of clusters, but of course many of them are encoding the same behavior, and you don't want to, if you go to someone and say, I have 300 benchmark points, you don't have any benchmark point, right? So, but there's also the other end of the spectrum where you start clustering, because you tell the algorithm to cluster, so you will merge two clusters, right? Despite them starting to get heterogeneous. Right? And if you have too few clusters, they'll be very heterogeneous, and then the benchmark point you choose inside won't really represent all the behaviors there. They get too different. Right? So you have to stop these, and this is kind of subjective. Huh? The good part of this is that if you do it, if you organize your code well, you can have a good visualization of this process. So you can see all these distributions for your whole parameter space of your model in an organized way. Right? And then decide when very heterogeneous clusters are appearing. Right? And in doing that, you also learn a lot about your model. Right? So I'll show some examples. And in the end, of course, once you're satisfied with the clusters, you do this comparison within the cluster to choose your benchmark points. Right? Then you can find it. Go ahead.
But this clustering is in one dimension only, right? You're showing it here as 2 dimensions, but you're clustering in 1 dimension. Namely, the only variable is TS, it's your distance thing, TS.
Exactly, and that's the beautiful part, actually. Because clustering techniques get really, really bad in multidimensional spaces. So if I was really trying to cluster a multi-dimensional space, this wouldn't work. The number of points that I wouldn't need here, that's a known fact, right? That clustering algorithms are really bad if you increase dimensions. It looks like I'm grouping because I can always go back to the parameter space and see what that forms, right? Where these groups formed, right? It's really hard because it's hard to plot 6, 7 dimensions, right? But the clustering is really happening in 1 dimension, and that's why it works, right? That's why choosing those kinematical distributions is better than actually looking at masses and widths, because then if you would cluster by mass, by width, by branching ratios, then you get again a multidimensional space, and your clustering might not work, at least not for any feasible computation time. Right? So at the end I choose these benchmark points, and that's it, that's the cluster, right? So now I'll apply this, right? So in this paper we apply this to the MCHM5, also to the MCHM14, but so I'll do a quick, really quick and dirt review what's the minimal composite Higgs model. So in this model the idea is essentially to make the Higgs composite, right? So you solve the hierarchy problem by saying, well, the Higgs is not really a fundamental scalar, so if you go above a certain scale, you start to see the structure of this theory, so it makes no sense to talk about Planck scale in these models, right? And you have also to include fermions in this model, right? And the way you do it, right, this is the Higgs will be goes from models from this breaking, right? And you include the fermions also as embeddings of this group. And you have some choice here, right? And what we call the MCHM5 is the choice to embed fermions as a 5 representation of SO5, which then, since you're doing this breaking, need to break into representations of SO4, right? And this 5 choice means you get a 4-plet of SO4 and a singlet of SO4. These are the composite fermions of your theory, right? But you also have fundamental fermions which come from the standard model, and the two of them mix. And that's the idea of partial compositeness, right? You have a mixing between these guys, and I'm highlighting their quantum numbers here. And you see they will mix with the left-handed 3rd generation, will mix with the right-handed top, also with the right-handed bottom, right? And finally, your top and your bottom are actually mixed states between fundamental fields and these composite guys. Right? So, for instance, in the charged 2/3 sector, you have these 2 guys coming from the 4-plet, this guy coming from the singlet, right? And also a fundamental field. Your Lagrangian looks like that, right? These guys are all vector-like, so they have their own masses, and that's the main scale of this kind of theories, right? You have one mass scale for the 4-plet, another one for the singlet, right? But they mix with the fundamental fermions through this part of the Lagrangian, right? And you have this mass matrix, which then you have to diagonalize, right? The constraint here is that whatever the eigenvalues of this matrix come out, right? You need one of them to be the mass of the top, right, of the standard model. But the other guys can be, they'll be heavier, but their masses depend on these parameters. Huh? And then the same happens with the bottom, right? So you have also a bottom partner, and isotonically charged top partner, right, with charge 5/3. And these are the parameters for this particular model, right? We have all this. This depends a little bit on how you absorb phases, right? In the choice we made, these are M4 is always positive, but M1 can be positive or negative, right? And one of these parameters is actually fixed by this demand to have the top, right? And we choose this last one, so you eliminate this guy, end up with these 4 parameters, with M1 being positive or negative. In the same paper, we also did the 14, but I'm not talking about the 14. I want to show the clustering of the 5 here. Right? In the 14, I'm embedding the fermions in a bigger representation of SO5, right? So you have a lot more partners and bigger mass matrix. This is just the charge 2/3 mass matrix, right? It's a much more complicated model. Right? So let's see how about the clustering. So to do the clustering, we essentially divided the parameter space, this parameter, in two regions, right? One where the scales, the mass scales are kept fairly low, right? Because we were thinking about searches in the high luminosity LHC, right? So here we had in mind the near future, right? And we did also another region where we allow these parameters to go much higher, right? With uncertain far future in mind, right? So looking at future accelerators. So we did for both these regions. I'll focus more on this one and then just show the results for the second one. So essentially what I want to do is organize this mass. Right? So in here what we did, we simulated PP to TTHH. This is mostly driven by the experimentalists, so we were in close collaboration with Aurore Savon-Navarro, and she's in a group that is actually looking for in the standard model for this signal, right? And she wanted to know what kind of new physics could contribute to that, and one main candidate is the composite Higgs. Right? And we generated a lot more points than these, but then you have to apply no constraints, right? You cut your parameter space with already excluded regions, and we were left with 348 points, and they are all plotted here. So here I show the invariant mass of the most energetic Higgs at the top. This is the PT of the most energetic Higgs, and all those curves are there, and you can see nothing, right? So the clustering helps in organizing these, right? So here I start to do the clustering, right? So I start to reduce 348 clusters down to, and this is one step where I stop at 300, and I'm showing the last 3 clusters in my vector. And you can see here the first kind of mistake you could make, which is making too many clusters, right? Even if I choose these black curves are the representatives, the benchmark point within that cluster, but I could choose the other curve because they are really homogeneous, but pretty useless because we have too many clusters. And this is the opposite end of the spectrum where you have 2 clusters. So I just divided those curves in 2. Already you see that there's some intelligent thing going on here because it's not random, the curves that are in one or the other, right? It separated the low-lying resonance from the heavier ones, but still really bad, right? If you take the black curve as a representative of the cluster, you're really not representing all of the points there.
What are the colors?
Well, there are essentially 4 colors here. So black is the benchmark point. Red and blue are these 2 regions. One is the region where these 2 masses have the same sign. Blue is the other one. And green is actually funny because it's the kind of benchmark point we would choose without doing any clustering. Right? So these are points that we choose in a part of the paper where we're just doing our usual thing, like going for the most easy to find thing. And you can see one here, in particular this point. Right? You can see it's the highest curve is equivalent to this one too. Right? And you see how good we are at choosing points that are at the same time easy to find, but not really representative of anything because it's lying really outlier, right? And this is the point that you'll probably choose if you just choose parameters, right? This green one here. There are 3 green curves there. They are messed with each other, but that's the point. Yeah? But really, what matters here is the black ones. Right, and secondarily, I'll talk a little bit about the red and blue ones because we found a difference between them. Yeah. So, just to give an insight on the method, right? As you go down, right? This is the step that goes from 12 to 11 clusters, for instance. Right? In this case, I'm just showing the invariant mass distribution, right? And this is what happened. Every step, you just merge 2 clusters. So we merge cluster 3 and 6 into cluster 11. Right? And this is the kind of merging that is improvement. Right? Clearly, there's no qualitative difference between the 3 groups that you see there. Right? And you have one less benchmark point. So you didn't lose a lot of behavior of your theory, but you have less benchmark points. Right? By contrast, when you go to from 11 to 10, what happens is you're taking a cluster that is already overpopulated, right? And because the algorithm is failing to find anyone similar to this guy, which is qualitatively different from that guy, right? It's not immediately obvious. You can see that on the benchmark point, but this group is concentrating most of the points where you have two near-degenerate resonances. So you have this two-peak structure in almost every curve here. That's not true there, but for lack of options, it's now lumping these two together. So you're losing this behavior, right? And more, step 9 would then take another big cluster and lump here. So at some point, and that's the weak point of this kind of approach, is that at some point you see like these black hole clusters is starting to develop, like the clusters that will swallow every other if you keep going forward, right? And that's why we stopped at 11, right? Also, there's a choice here, I didn't comment. We choose these two distributions, so the invariant mass of this is the highest energetic Higgs, right? But as his question already prompted, right? It didn't matter too much which distributions I chose because my final state is too simple. They are all really correlated, right? So you see that in most of these plots, I use these two distributions as a criteria for clustering, but I didn't use this one as a criteria. And still, the clustering is good even in the distribution I didn't use, right? Because they are correlated, right? So this is the final thing. So we stopped at 11 clusters, right? I'm showing just 6 of these clusters to highlight some of the things that we saw, right? So the first one is this separation between blue and red. Right? So many of the clusters that showed up were dominated by red or blue, right? Which means that there is a different behavior in these two regions, which, at least to our knowledge, is not expected, right? One thing that people have commented before, but we didn't know, is that in general, the red region resonances are wider. You can see that comparing these plots to these ones, especially because there are some blue curves there, and you see that the blue resonances are narrower, right? And then we learned that through the clustering, because it's organizing all that mass, you can actually see your whole model in these plots, right? You're looking at the whole parameter space at the same time by looking at plots like that, right? And we noticed that, but then by going to the mass matrix, we understand why that was happening, right? Also, another thing that came out of this is that the usual simplified assumption that we use for top partners, which is something like that, right? I have one really light top partner and nothing else, right? Is very rare. I think we have one cluster that it looked like that, and all the others were more messier, having many resonances close to this one. So it's kind of fine-tuned in the sense that it's a small region of the parameter space to assume that you have big splitting between these partners. And that's what all the searches did, right, so far, looking just for one guy. Right? Usually you have many. So this is too many numbers, don't try to read all of them. Right? These are all the clusters, so all the benchmark points. So I have 11 clusters, so each column here is one benchmark point. Right? These are the Lagrangian parameters, and here is the spectra, right, of the top partners and the bottom partner and the exotic guy. Right? And we noticed a few things here. So the first one is that story, also they are colored by the region red, right? So one thing is that in region 1, right, the couplings, the mixings, are going towards the strongly coupled regime. You see, you're basically at the upper limit of what we allowed. And that's happening because of the mass of the top, right? Essentially, the mass of the top is proportional to the difference between N1 and N4. And so if they have the same sign, that number becomes small, you have to increase the coupling to get the mass of the top. And that makes these resonances wider because they're more strongly coupled, right? So in that region, you have wider resonances because of that, right? The second thing, and this is more important, is that the usual, every experimental search for the top partner and also for the X5 assumes they decay into these 3 channels. Then you can do a lot of combinations of these branching ratios, but every search so far assumed the sum up to 100%. And you see that of 11 benchmark points, that only happens in 1 of them. In all the others, the 3-body decays are important. And that has a lot to do, it's very related to the fact that we have degenerate states close to each other. Right? So you have a 3-body decay that goes through the exotic guy.
So eventually, in this case, how did you decide when to stop clustering?
Well, that was the point. I could go forward, right? But I would be lumping groups that are, you're losing resolution, right?
But
you're losing resolution.
Let's say that you just look at the plots you showed us and decide by hand, okay, this is a good time to stop, or was there some other?
By hand. It was really a decision. You're looking at different clustering. You can see all of them at the same time, and you decide essentially what looks better. Right? You could probably put another layer of statistics to make that decision too, right? But we didn't do that.
Okay, so you don't think there's a big advantage in automating that?
Yeah, exactly. Yeah. So the point here is that people are not looking for this 3-body decay, and it could be really important for top partners. Right? And of course, it changes. You could recast the searches that we have today in order to see how that changes if you relax the saturation assumption that they made, right? Like these 3 branching ratios add up to 1. We are actually doing that right now. Right? Trying to see how that would change the present day exclusion for the top partner, which is around 1.3. And also another thing that you see here is that the B channel is really suppressed in most of these cases. We did the same for the high scale part. Some things become more clear here. So now we're allowing these parameters, especially these 2 mass parameters, to go much, much higher, right? And the same kind of behavior shows up. You see 3-body decays become important, right? In some cases, you have exactly what you expected for these 3 decays, right? In top Higgs, WB, and TZ, right? But you see how important the 3-body decays is becoming, right? So if you want to push the exclusion of this guy, now it's 1.3, right? If you want to push it to 3 TV, say, you see the 3-body decay is starting to dominate. Right? So it will be really important to tackle these. Another thing that becomes clear once you allow these scales to go up that much is that it becomes really obvious which mass is controlling those lowest lying states. And then you see that when these guys, basically the lightest top partner is essentially coming from the singlet, then you have the naive expectation, right? But when it's coming from the fourplet, right, is when you have this behavior that suppresses the WB and leads to very big 3-body decays. You have some really degenerate cases here, right? And then these states probably tricky to look for because they are all on top of each other and really wide. We're also exploring how to make like inclusive searches to look for these guys, because maybe you can profit from having all these states on top of each other if you don't try to separate them and just look inclusively for signal of these new physics, right? Also, very important point is it's all well and good when you find these benchmark points and say now we have benchmark points, experimentalists should go and look for them, right? But if no experimentalist actually looks for them, it's not that fun, right? So we're happy that this collaboration actually led to a search by CMS. So these 2 points, the C2 point is one of the points I just presented, right? D7 is one that comes from the 14 that I didn't present here, but is on the paper. And these 2 points are actually being used. We actually gave them the model files, we helped them with the start of the simulation. They're taking the analysis forward with these 2 benchmark points. Here compared with the standard model for this top Higgs searches, right? Both in this innocent cut and count analysis, but also in more serious neural network things that people do, right? And they actually, this is in the Snowman's white paper for 2022, but they also released a public note which is more complete. And this is the prospective, the expected exclusion limits for 3000 inverse phantom arms for the high luminosity LHC. So they are actually running this point C2 and point D7 in a serious experimental analysis, which is, pleasing to see, at least being used as it's supposed to, right? So I try to keep it short. It's okay. So these are the conclusions, right? So the main takeaway message is, if we really want to say there's no new physics, we have to look away from the lamppost, right? Maybe we feel that there will be nothing away from the lamppost, but that's not how science works, right? You have to look and you have to exclude all possibilities, otherwise you will always be left with these blind directions that you never explored, right? And smart algorithms can help us do that, because it's really a tough work, right? Regarding the top partners, these are the two messages, right? We have for future searches, we'll have to look into three-body decays, because they become more important as the guy gets heavier, right? And also taking a simplified spectrum where you have just one low-lying top partner is not good enough, right? It's just fine-tuned. The model in most of its parameter space has a lot of these resonance is split by small weak splittings, right? There's no reason they should be apart, right? And that's all. Thank you for the attention.
Ricardo, thanks for the talk. Quick question. Did you implement this clustering by yourselves manually? Because there are plenty of clustering algorithms in the market, right?
We did it ourselves. That's part of trying to learn the thing, right, too. So we actually have two codes to do that, because I implemented it in Mathematica first. I did the 5, and then a student tackled the 14, but he preferred Python. So instead of using my code, he did it everything again in Python. I don't know, he wanted to learn Python. So we have this code basically twice. The plots you see here were all done in Mathematica. Yeah, essentially, let me go back. This log likelihood is what is being used to judge how alike these curves are, right? And there's a lot of, I wouldn't be able to defend these properly, right? But if you go to this paper, they have a lot of arguments why this is the best one to measure. A few things that you can see here, right? You could use chi-square, but most of the distributions we're looking have a very different scale. So the number of events here is orders of magnitude smaller than the number of events here. So if you just use chi-square, this will be dominated by small differences up here. That's not good, because most of the interesting stuff is happening at higher low count beams, right? Higher energy low count beams. So being log is advantageous in that respect, that compensates for these, right? Oh, I think it's a Bayesian analysis, right? But I wouldn't be able to defend this particular likelihood properly, right? So I won't even try.
So yeah, I'm curious again about the question of why using one-dimensional distributions. Because so recently we actually looked into something in a similar direction, where we were arguing that instead of doing what we usually do of exploring parameter space, picking new points, and then integrating you could do is promote model parameters to the same level as what you treat phase-space parameters, and important sample everything. So you're basically doing a phase-space integral over model parameters as well, using importance sampling. And what you get at the end is this big, you hear called test statistic or your likelihood, over the whole of the parameter space that we use to build a KDE, like an interpolation method, but you could use to just build arbitrary n-dimensional distributions that give you a number. That could be your likelihood or so. So I guess the point is that you don't need one-dimensional things. You could just have the whole, I mean, you could have a Monte Carlo slice for each point parameter space, and you can represent that as an n-dimensional distribution or just n number of events even. Like that would be, you know, however many points are able to sample around a neighborhood in that model parameter space. So
Yeah, you're probably right. I mean, it's worth, I think it's something worth trying, right? The one caveat I see here is the one I mentioned to Thiago. I mean, the bigger the dimension, the worse clustering algorithms are.
but your clustering
So you have to
your clustering would still be one-dimensional, as you mentioned, because you're still using the test statistic.
which is this one number, right?
Yeah.
Yeah.
What makes it more expensive is then your computation of the test statistic may be hard. But if that's not what you're doing.
Yeah, that's. I mean, the horsepower, computational horsepower needed here is to actually run MadGraph 500 times for fixed luminosity, right? That's where everything you do afterwards take hours, right?
And the problem with these fancy techniques is that then tools are not adapted to do them. So there's no way to tell MadGraph integrate along theta or theta sum in the same way that you would phase-space variable.
Yeah.
Yeah, it's harder to do, but in principle, it gives you as much information as you can simulate.
Yeah, maybe we can talk about that later. Give me some references. It's something maybe, yeah, we'll try.
Yeah, thanks for the talk.
Oh, no problem.
More
Okay.
Fez isso pelado, tipo, olha
Não, então, mas é que tem aí uma graça de fazer. Eu gostei. Legal, um negócio legal de implementar. Vem do zero. Sentei e falei,
deixa eu
vai dar uma.
Eu vou dar aula.
E como você está usando?
Não, tira tudo. Fora.
Eu acho que faz para.
Você está gravando ainda?